Okay, in this video, I'm going to be explaining how monotonic stack works. So, basically, we use this stack, and basically, a monotonic stack is just a stack that we always keep in order. And the way that we keep it in order is by either by just popping off elements that don't conform to the order. And so we can have a decreasing monotonic stack as well as an increased monotonic stack. So increasing would be if we're trying to keep the order increasing. So like if we have numbers 1, 2, 3, and 4, and then decreasing is just the opposite if we want to keep it in a decreasing order. So the best way to really quickly understand just how we keep the stack in order is by just going through an example. If we just have a stack here, and let's say we're given input 2, 1, 6, 3, 5, 4, and we'll just say another 2. So let's say we're trying to keep this in increasing order. So first, we would just, if the stack is empty, then we can just add the element in. So 2 would just go onto the stack. And then next, we want to keep it in increasing order. So basically, once we reach this 1, we're going to check if this 1 is actually bigger than the element that's on the top of the stack. Or sorry, if this 1 is smaller. And if it is smaller, then this element is going to get kicked off the stack. It's going to get popped off, and 1 is going to take its place. And so it will be 1 here. And then we're going to check if 6 is smaller than 1. And it's not, so 6 can just be placed right on top of the stack like this. So it's still in order. And then now we have a 3. So we can see that the 3 is smaller than the 6, but not smaller than the 1. So only kick off the 6. And so now we have 1, 3. And then for 5, 5 is bigger than 3, so it'll be put on. 4 is smaller than 5, so 4 is going to kick the 5 off. And so we'll have 1, 3, 4. And then now we back at the 2, and we can see that 2 is bigger than 3 and 4. So it's going to kick off 4, and it's going to kick off 3. And it's just going to be 1, 2 at the end. Now, the reason why this method of using a stack like this is really helpful is because the elements that get kicked off and the elements that an element is placed next to basically allow you to find the next greatest value, and to the right and to the left for a decreasing monotonic stack, and the next smallest value to the left and to the right for an increased monotonic stack. And let me show you what I mean. So first of all, if we keep with this example, 2, 1, 6, 3, 5, 4, 2. And let's say we want to find the next greatest element for each of these numbers, right? So for example, for 2, the next greatest element would be 6, since 2 is smaller, or 2 is bigger than 1, so this is not greater than 2, but 6 is bigger than 2. So this is the next greatest element to the right. And for 1, the next greatest element to the right is 6. For 6, there is no next greatest element. For 3, it's 5. For 4, there is no, or sorry, for 5, there is none. For 4, there is none, and for 2, there is none to the right. And then of course you can do the same thing for going to the left. But basically, in order to find the next greatest element going to the right, it will be whatever element pops off a certain element off the stack in a decreasing monotonic stack will be the next greatest element to the right. So let's just use a stack here. And for example, we're just going to go through it and put 2 in. And since now we're decreasing, so now we want the stack to be going from large to small, basically like 4 to 1 if we were having something like that. But anyway, so we put 2 in. Now 1 is smaller than 2, so 1 is allowed. And then now we have 6, right? So notice how 6 is going to pop both 1 and 2 off the stack. And it also happens to be both of their next greatest number, right? And so if we can just find a way to keep track of that, then we can basically map and basically know that 1 and 2's next greatest element is this 6 here. And so like you can just see like this behavior will be replicated. So it's going to pop it off the stack and there'll be 6 and then 3. And then you notice how 5 is going to be popped off, or 5 is going to pop 3 off the stack, and 5 is 3's next greatest element to the right. And so if we continue, 6, 5, 4, 2, and notice everything left in the stack doesn't have a next greatest element, right? This 5 doesn't, this 4 doesn't, this 2 doesn't, at least to the right. So they weren't popped off the stack, and so they don't have a next greatest element. Meanwhile, if we want to find the element that is the next greatest to the right, we just have to keep track of what element is underneath you as you enter the stack. So as this 1 enters the stack, the 2 is underneath. While the 2 enters the stack, there's nothing underneath, so it means that it doesn't have a next greatest element to the left. And so when the 6 enters the stack, same, nothing under it. So, and then, but when this 3 enters the stack, there is a 6 under it, so it knows that the 6 is the next greatest element to the left. And so this works exactly the same for increasing stack. So if you use an increasing stack where it goes 1, 2, 3, using this will give you the next smallest to the left and to the right. So in this case, we used a decreasing stack, so it gave us the next biggest. So you just kind of have to remember that it does that. So now we can just go over and review a problem really quick. Okay, here we go. So we're going to go to a we're gonna just start off with a decently difficult problem. Explained pretty quickly. So this problem is to find the next, or to find the largest rectangle area. And given an array, we have to find which rectangle here is the largest. So you can make a bunch of rectangles. You can make like this rectangle. You can make like this rectangle. But what we do notice is that all of these rectangles, like we can kind of look at the largest for each one. So for this one, this is the largest one this can make. For this one, it's this long thing, and then for this one, it's this one. For this one, it's just itself. And the largest rectangle has to be within one of these rectangles because these are the largest rectangles that each one can make. And so the largest rectangle of them all is just the largest rectangle of all of them. So now how do we use the monotonic stack in order to find out how to make these rectangles? So we'll notice that for every single element here, as long as we can find the next smallest element to the left and to the right, we can know our constraints of how big the rectangle should be. And so this is how we use the monotonic stack. If we go look at this solution here that I wrote. So basically we make 2 arrays and we keep track of the smallest to the right and to the left. And we also have a biggest area, which we will use later. So in the first part, we just initialize everything to -1, just in order to be able to find, to see which ones haven't been initiated. And then from here, we basically use the monotonic stack, and we pop off everything we pop off. We're going to store, we're going to basically store the one that we popped off, and for the thing that gets popped off. So like if 6 pops off 1, then we know that 6 is the next smallest element for 1, or next greatest. But in this case, we're using next smallest. And so we're going to store that, and we're going to also store which one is before once it enters the stack. And we create these 2 arrays of the smallest and the largest, or sorry, the smallest on the right and the smallest on the left. And from there, we can kind of create this bound, basically the x-axis, and we just multiply that x-axis for each element versus its height, which is just going to be the height of the element. Since we know that as long as it doesn't hit something smaller than it, it's going to be at the same height. And so we can just keep that as long as we can until we find something that's smaller. And then we just basically have this biggest area that we keep stored. And at the end, we just return biggest area. So that's just a solution with the monotonic stack.